This is the sixth lecture on Hamiltonian mechanics. In the earlier lecture, we have introduced Poisson bracket and discussed about the properties of Poisson bracket, and we also discussed the fundamental Poisson brackets and found the make an analogy with the corresponding relations in quantum mechanics involving commutator bracket. Finally, we have evaluated the commutator brackets of variables q's and p's with h and has written the Hamilton's canonical equations in a symmetric form. Finally, we discussed the equation of motion of a variable and discussed the condition in which a quantity dynamical variable becomes a constant of motion. Today we shall discuss the Poisson bracket involving angular momentum. So today our topic of discussion is Poisson bracket involving angular momentum. In fact, we shall consider angular momentum in Cartesian coordinates or its component in Cartesian components because they have the simple relations. Before going that, recall in quantum mechanics. In quantum mechanics, we found that L alpha Q beta is equal to RH cross epsilon alpha beta gamma Q gamma. Then if we write this is P beta, then L alpha P beta is equal to RH cross alpha beta gamma P gamma, and finally we had L alpha L beta is equal to RH cross epsilon alpha beta gamma L gamma. These relations, this quantum relation we have derived in our earlier classes on quantum mechanics. Today we shall derive the corresponding relations in classical mechanics using Poisson bracket. So first, what we shall do, we write the expression of the Cartesian components of angular momentum. So we write L is equal to summation over I is equal to 1 to 3 EI cap Li. So Li is the Cartesian components. Components of L vector. In quantum mechanics, they were operators. So L alpha, this simple expression for L alpha, we know that it is epsilon alpha beta gamma Q beta P gamma, where epsilon alpha beta is the Lebesgue beta tensor, and it is 1, 2, 3 is equal to epsilon 3, 1, 2 is equal to epsilon 2, 3, 1 is equal to plus 1, epsilon 1, 3, 2 is equal to epsilon 2, 1, 3 is equal to epsilon 3, 2, 1 is equal to minus 1, and other combination, for other combinations it is 0. So we make a simple calculation. L alpha Lx, we know that Lxx in this notation it is basically L1 Q1. So this is Lx is ypx, sorry, this is ypz minus zpy times x. So this is the combination of two Poisson brackets. First one is this ypz by ypz of x minus zpy x. This is splitted into two pzx plus yx pz, then pyx minus zx py. Each of the elements are 0 because we recall that q alpha p beta Poisson bracket is delta of alpha beta, and q alpha q beta is 0, q alpha q beta is 0 is equal to p alpha p beta. So this relation is 0. If we now change x, this x by y, the changes will be these will be the changes, and you see that this is again 0, this is 0, this is non-zero, this is 0. In fact, this part is minus 1, so this makes it plus. So Lx y is actually minus x plus, this is plus z. And if we replace this relation by z, the corresponding changes will be, this will be z, this will be z, this will be z, this will be z, it is z, 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 this is z. This is 0, this is 0, this is 0, only term is this. This will be minus 1. So Lx z is equal to minus y. So there are altogether 9 such results. We can derive all these 9 results by using the compact notation this. We shall derive this one, L alpha, L beta. As you are already habituated with the Lebesgue-Beta tensor and its use, so I am not going to elaborate the things. L alpha q beta. So for L alpha we write epsilon alpha, already beta is there, so mu nu, q mu, p nu times q beta. And here we have used Einstein's summation convention. Here in the index, dummy index mu and mu are repeated, so sum over mu nu is implied. So this is epsilon alpha mu nu. This is q mu, p mu q beta plus q mu q beta q beta p mu. This part is 0 for all combinations of mu and beta. This is 0 identically, and this part is minus delta mu beta. So we have minus epsilon mu nu delta of mu beta q mu. So if we carry out the sum over mu, then mu is replaced by beta. So we have epsilon alpha mu beta q nu. We just interchange the ordering and we write it epsilon alpha beta mu. This is q mu, and there will be a minus sign adjusted. So this is the single derivation which accounts for all 9 relations. Alpha may be 1, 2, 3 and beta may be 1, 2, 3. So all the 9 relations are coupled together in a single derivation. So in the simple derivation that we have done, we evaluated Lx x found to be 0. If you come to this relation, this is basically epsilon 1 1 gamma q gamma. Because the index are repeated, so it is 0 identically. Then we have Lxy. Lxy is equal to epsilon 1 2 gamma q gamma. So for non-repeated index x, this should be 3, and we have epsilon 1 2 3 q3. You know that epsilon 1 2 3 is positive 1, so this is z what we are obtained. And finally we have Lxz, and Lxz we have 1 3 gamma q gamma, and for non-repeated indices this should be epsilon 1 3 2 q2. 132 is minus 1, so this is minus 1. These are the relations which we have obtained by elementary derivation, and this is a compact derivation which incorporates all 9 such relations. Now we come to the relation for p's, L alpha p beta. Then for L alpha p beta we replace this by p beta, and this is p beta, this is p beta, and we have this is p beta, this is p beta. This is the chain, and the relation is, this relation is 0 identically, and this is mu beta. So from here we will have a different derivation. So we have alpha mu nu delta of mu beta p gamma, p nu. And if we carry out the sum over mu, we have mu will be replaced by beta, so alpha beta nu p nu, which can easily be written as alpha beta gamma p gamma, as the dummy index may be changed. Now finally we come to the complicated relation, that is P alpha, L alpha, L beta derivation. And before doing that, we shall remember the 2 relations that we have already derived. One is L alpha q beta is equal to epsilon alpha beta gamma q gamma, and L alpha p beta is equal to epsilon alpha beta gamma p gamma. So our daily requirement, we want to prove L alpha L beta. To enable us to write this relation directly, we write it as L alpha epsilon beta mu. For L beta we write q mu p mu. So this is epsilon beta mu. Then we have 2 terms. One is q mu L alpha E mu plus L alpha Q mu P mu. These are the two relations. You recall that this part is epsilon alpha mu, then we introduce delta, E delta, and for this it is epsilon alpha mu epsilon Q epsilon. So we have, for the first term there are two epsilon beta mu nu, this there was a wrong, it's mu. The second index was mu. Beta mu, then this comes alpha mu delta Q mu E delta. Then from this, for the second term, epsilon beta mu epsilon alpha mu epsilon Q epsilon P nu. Here we bring this nu in the first place, so we need to have two interchanges. One is that is we have beta mu. From this one interchange we get beta mu. In the second interchange we get it mu beta mu. So it will involve no sign, change in sign. We have mu beta mu. And if we want to bring mu in the first place, then there will be a negative sign. So it will be epsilon alpha delta Q mu E delta. Similarly, in these two delta epsilons, the repeated, we shall bring the repeated one in the first place. So here the repeated index is mu. If we bring mu, here we will have a negative sign and there will be another negative sign. So it will be epsilon alpha beta mu, and this will be epsilon mu alpha epsilon P mu. You know that when this new sum is carried out, we have two delta functions. The positive delta function will be delta of alpha beta, first with first, second with second, and third with third. And with the minus sign, second with third, you are acquainted with this properties of divisivity. Then coming to this, first delta functions are alpha beta, and then delta of mu epsilon minus delta of beta epsilon, delta of alpha mu. Now if we carry out this term, then we find that mu and delta will have the same value. So we have minus delta of alpha beta, and we write it Q mu P mu. This is from the first term. This delta function has been operated, so one sum is removed. So there is a sum over mu only. These two things makes this two negative sign makes it positive. If we carry out the sum over mu will be replaced by alpha, and similarly delta will be replaced by beta. So it is q alpha p beta. Coming to this term again we see that one of these sum will be removed and the other one, and we have delta of alpha beta p q nu p nu and for the second term it is epsilon will be replaced by beta, so this is q beta, and nu will be replaced by alpha, p alpha. The meaning of these two terms is that only when alpha is equal to beta, these two terms arises, otherwise they are zero. Even if they arise, this is the sum over q mu p mu, that is this is q1 p1 plus q2 p2 plus q3 p3. Similarly thus, so these two terms cancels out. These two terms will arise only when alpha is beta, otherwise this will not arise. So the result is q alpha p beta minus q beta p alpha, which is epsilon alpha beta gamma L gamma. So we have proved all these relations involving the Cartesian components of angular momentum, the Poisson brackets. We have evaluated the Poisson bracket involving the Cartesian components of angular momentum. The relations look very similar to the corresponding quantum relation. Only thing is that in quantum mechanics the dynamical variables are operators. The ordering do matters over there. In Hamiltonian mechanics or in classical mechanics, as they are variables, ordering doesn't matter. And that in quantum mechanics there was a very important role played by the Planck's constant, which is which introduces the quantization, and here in classical mechanics, as there is no quantization, there is no H. That's all of Hamiltonian mechanics.